Hi. In the previous podcast, we developed analytical solutions for water transport problems during infiltration. And we made these developments for horizontal and vertical infiltration problems and for soils considered being linear soils, green and amp soils, and realistic soils. With the analytical models, we can predict measurable properties such as infiltration rate in terms of soil physical properties such as sorptivity. But we can also invert these simple infiltration models and predict the soil physical properties such as sorptivity or hydraulic conductivity or diffusivity in terms of measured infiltration rates. Hence, a popular application of analytical models is infiltrometry, which is the methodology developed to estimate soil hydraulic properties from infiltration experiments. One of such popular measurement technique is the double ring infiltrometer technique. It is popular because it is rather simple to implement in practice. Have a look, for instance, to the demonstration shown in the YouTube link film which is projected in the slide. It is a demonstration developed by the commercial company Ekelkamp. The double ring infiltrometer forces water to infiltrate from two separated reservoirs at the soil surface. Yet the fact that the central reservoir situates inside the external reservoir implies that the flow below the central reservoir will mainly be vertical. The infiltration from the central reservoir in the double ring experiment allows therefore to simulate in situ an experiment for which an analytical solution exists. For instance, we can apply a constant head in the infiltrometer and set this head at very low value to simulate the condition close to the condition for which the Philip infiltration model is valid. So, if we can measure cumulative infiltration rates as a function of the square root of time, and if we plot this, we estimate directly the sorptivity of the soil from the slope of this curve. If we subsequently determine the initial and saturated soil water content, we have an expression of S as a function of theta S and theta I. In many hydrological textbooks, it is suggested to use the steady-state infiltration rate measured with the double ring experiment as a proxy of the saturated hydraulic conductivity of the soil. From previous podcasts, we know that this will induce some error, as the long-term infiltration rate in the Philip model will be smaller than Ks. It is therefore expected that we can easily make an error of nearly 30% when assimilating the steady-state infiltration rate A to Ks. Yet, this error is still often acceptable in practical applications, given that the Ks, the hydraulic conductivity at saturation, may vary different order of magnitudes within the field. Yet we can apply a more rigorous analysis and infer more information from the infiltration experiment when determining the sorptivity from the early time of the infiltration experiment. Indeed, from the previous theory, we know that S is a function of the initial water content and the hydraulic properties of the soil. For instance, an expression given in soil physical literature on sorptivity is given here. It shows that S, which we can infer from the double ring experiment, is determined by the diffusivity and the value of the initial water content and the saturated water content. It is also dependent on a shape function, f theta, which is related to the shape of the soil water profile below the infiltrating surface. The expression here is given for a soil water head at the infiltrating front, which corresponds to h equals to 0. In case the water level is larger, which generally is the case in a real infiltration experiment, we could use this formula. The formula here is still a bit complicated for practical application, as it implies knowledge of the shape function f, and it implies the calculation of an integral of a strongly nonlinear function based on the hydraulic conductivity or the diffusivity curve. We are therefore going to simplify this equation a bit. The first simplification is that we are going to introduce another auxiliary property the matrix flux potential, or the Kirchhoff transform. It is an integral transform function of the hydraulic conductivity curve. It corresponds to the total area below the hydraulic conductivity curve bounded by 0 and HI on the pressure head axis. It will be therefore 0 when the initial soil is saturated, and it will be high when the soil is dry. With this integral transform, soil physicists developed an approximate solution of the sorptivity equation in which a general parameter, the so-called Sully parameter, appears. It is shown that this Sully parameter is rather soil invariant and situates between 0.5 and 0.878. And this is an interesting equation since we have now one equation and two unknowns, Ks and Pcm. So if you really would like to determine the hydraulic properties rigorously, we need to perform at least two infiltration experiments, for instance, for two values of H. If we do this, we can obtain two values of S, each for a given H, and hence to apply the shown equation two times to estimate Pcm and Ks. If we perform more measurements, we overdetermine the system and can obtain Pcm and Ks from classical regression. But we can go further, since in previous formula we express S in terms of Pcm and Ks. If we apply some hypothesis on the shape of the hydraulic conductivity curve, we can obtain a simple expression of Pcm. Indeed, if we consider that the soil can be modeled with the hydraulic conductivity model of Garner, then Pcm simplifies to the ratio between Ks and alpha, where alpha determines the slope of the hydraulic conductivity curve. Hence the resulting equation is given below. Also, the slope parameter is very often soil type invariant. If we use generic values of alpha, then we have an equation with just one unknown, Ks. So, given S, Cs, Ci and H, we can estimate the value of Ks. Such analysis is more rigorous to estimate Ks of a soil as compared to the estimate of Ks from the long-term steady-state infiltration rate. In previous slides, we considered the analysis of the double ring experiment, and we considered that the flow was essentially vertical. We can also make infiltration with single ring infiltrometers. In this case, however, the flow below the infiltration disk is no longer essentially one-dimensional. We need therefore to apply other analytical solutions. In case of infiltration from a single ring infiltration device, we can rely on the Wooding equation that allows to calculate steady-state discharge Q from a single circular source. In Wooding's equation, the steady discharge Q is calculated in terms of the matrix flux potential Ks and geometrical properties of the infiltrometer. Dividing the discharge by the surface area of the infiltration disk allows calculating the steady-state infiltration rate I. If we consider a hydraulic conductivity curve that is modeled by means of the Gardner exponential model, we obtain an expression of the steady-state flux in terms of two parameters, Ks and alpha, and also some geometrical parameters like R and H. So if we want to obtain alpha and K, we need to carry out two infiltration experiments. For instance, we can perform an experiment with two different pressure heads in the infiltrometer H1 and H2. We will in this case obtain two equations with two unknowns. Alternatively, we can also perform an analysis with infiltrometers with two different radii. A more advanced and practical approach is a pressure infiltrometer, as shown in this figure. In this case, the water infiltration bulb will be deformed as compared to the expected bulb below a circular disc. This deformation will depend on the depth of the insertion of the water reservoir. The pressure permeometer is coupled to a Marriott device, allowing to maintain a constant head at the soil surface. With the positive pressure at the soil surface, we need to adapt our definition of the matrix flux potential as shown in this figure. We add a component due to the additional pressure developed in the reservoir of the permeameter. We further introduce a correction term in the Wooding equation to take into consideration that the permeameter will deform the wetting bulb as compared to a wetting bulb from a perfect circular object. The correction factor will be a function of the geometrical properties of the infiltrometer, D and R. With these corrections, we obtain the adapted Wooding equation that we can use to analyze the experiment. As in the previous analysis, we measure a steady-state infiltration rate Q, and if we want to know the corresponding hydraulic properties, carry out the infiltration at least with two different parameters or with two different disk radii. A last device that often is used is the suction infiltrometer. The interesting thing about this device is that the water reservoir and the soil surface is separated by a semi-permeable barrier. It is a piece of nylon cloth or a ceramic plate. The barrier allows retaining water by capillarity. In this case, a negative pressure can be imposed at the soil surface, but this negative pressure is still higher than the negative pressure in the soil. As a result, the water will not flow when it is not in contact with the soil, but as the water will be retained by capillarity in the separating barrier. The interesting thing of this is that unsaturated flow can be imposed during the infiltration experiment. This is particularly important for a good characterization of flow in structured soil. With the suction infiltrometer, you can exclude macropores participating into the flow. The analysis of the suction infiltrometer again relies on the Wooding formula. In this case, the matrix flux potential needs to be adapted to consider only the porosity of the soil that effectively participates to the unsaturated flow. In this condition, we integrate the hydraulic conductivity curve between HI and the initial suction head of the soil below the infiltrometer and HA plus L, the suction head that is imposed at the soil surface. So, with these examples, we have seen that analytical solutions of the governing flow equations have many examples in hydrometeorology. Analytical solutions of the infiltration problem can directly be applied to interpret infiltration experiments and assess the hydraulic properties of soils in situ. We should, however, well acknowledge the limits of analytical solutions. They are only applicable to interpret simple flow experiments or to make predictions of the water transport process in the soil when the soil is subjected to simple and constraining boundary conditions. Hence, if we want to simulate more realistic conditions in operational soil and water engineering, we need more flexibility. Therefore, we are going to develop numerical techniques that can be applied into more flexible conditions. Before launching into these alternative techniques, please have a look to the field theory of the previous chapter as given in the syllabus of the course.